Good morning, all. I will request Shauli Gur, who is the chair of the Indian Women in Mathematics, to tell us a little about Indian Women and Mathematics as a collective and its activities around the year. And then we will start with the mini course. Okay, over to you, Shauli.
Thank you, Anisha. So I will try to keep it brief because I think there are a lot of people who are waiting for the lecture, including me. Let me say a few words about Indian women and mathematics. It is a collective of Indian mathematicians that has been in existence since 2009. And our mission is to encourage women to take up higher education. And we generally organize events and provide networking opportunities that helps women to take up careers in mathematics. So we are currently 14 members in the executive committee of this Indian Women and Mathematics, which consists of both male and female members. So the details of this, one can look up in Indian Women. If you Google Indian Women and Mathematics, you can easily get our website. So let me say when it started, in 2010 in ICM Hyderabad, there was the first international conference of women mathematicians was planned. And just before that in JNU, a conference was organized where participants were mostly women and 2/3 of the speakers were women. And this conference before just ICM, the International Conference of Women Mathematicians, one of the speakers, just to give you an example, encouragement can go a long way. One of the speakers was Maria Mirzakhani, who went on to win the Fields Medal 4 years later. And then over the years, after that, in 2012, there was a symposium which was organized by Joya Iyer and Baijanti Chari in IMSC, Institute of Mathematical Sciences in Chennai. And that was the starting point when the government organization started, in particular, National Board for Higher Mathematics, decided to support the activities of Indian women and mathematics. And since then, it has been supporting us continuously. And we are thankful for that. So another support came from international Community for Women in Mathematics, which is a part of our International Mathematics Union. So this gives us an international flavor. So we organize several programs. Some of the programs, annual conferences, one annual conference, regional workshops, visitor program, winter school, and online mini course. This online mini course was started during pandemic, and the idea is to have speakers who are established speakers and a speaker who can deliver lectures which is accessible to a wide range of audience. And they generally deliver a set of 4 lectures over the weekend. And this has been a huge hit. And we also have these lectures. One can look up for this lecture in IWM YouTube channel. So last few years, it has been going on. And what we want to continue in this direction, have many more programs. And one of the new program we are excited about this year, which is going to happen, research in groups, which we are planning in December, where we will take up projects where people will learn advanced topic and then they go on. I mean, they will later on will start, if they are in a position to learn enough mathematics, they will take up research problems as part of that program, which will be a year-long program. So, okay, without taking further much any more time, I think I will give it back to Anisha so that the lecture can start. Thank you.
Yeah, thank you, Shauli, for giving us this information about IWM and its activities around the year. So I now present to the audience Tejas Kalirkar, who is a colleague of mine here at ISER Pune, and he is a topologist himself, and he has kindly agreed to moderate and chair this session. So I request Tejas to introduce the instructor, Professor Mahan Maharaj, and take over the session from here. Yeah, over to you, Tejas.
Okay, thank you, Anissa. Yeah, so welcome everyone to this session on geometry and topology by Professor Mahan. We are really fortunate to have Professor Mahan teach us about geometry and topology, because in the field of geometric topology in particular, Professor Mahan really lives up to his name. Professor Mahan completed his master's in mathematics from IIT Kanpur and then went on to the University of California in Berkeley in USA for his PhD. He then returned to India and joined the Ramakrishna Mission Vivekananda University, where he was the professor of mathematics and the dean of research till around 10 years back. And then he moved to the Tata Institute of Fundamental Research in Mumbai, where he's now a professor of mathematics. Professor Mahan is a recipient of prestigious awards such as the Shanti Swarup Bhatnagar Award and the very prestigious Infosys Prize for Mathematical Sciences. He's also been an invited speaker for the International Congress of Mathematicians, which is considered a great honor in the mathematical community. He has made significant contributions to various fields in geometric topology, including hyperbolic geometry, geometric group theory, and the broad area of low-dimensional topology. His most famous work, in fact, is proving the existence of Cannon-Thurston maps for Kleinian groups or for hyperbolic spaces. And this problem, in fact, was one of the famous open problems listed by William Thurston, one of the 24 open problems that Thurston listed. And Thurston, of course, is one of the founding mathematicians for the field of modern low-dimensional topology. So one of these open problems was resolved by Professor Mahan. So yeah, so without taking up any more of your time, I'll hand it over to Professor Mahan. Thank you.
Yeah. Thanks a lot, Tejas. Am I audible?
Yes.
Great, terrific. Yeah. So thanks very much, Tejas, for this very kind introduction. And it's a real pleasure to be able to say something in this terrific initiative of Indian women in mathematics. I mean, I think as practicing mathematicians, we all know and understand that in principle, mathematics as an endeavor is completely agnostic to people's gender, belief systems, nationality, etc. All that is irrelevant. But the practical situation on the ground is not such. So I think initiatives like this are excellent in order to finally live up to the ethos that the subject puts forward, that it is completely inclusive of all people. Okay, so terrific. There is a little bit of a change that I took the liberty of doing, which is basically flipping the order of the first two lectures. So let me just say how we have decided to organize this. So the lectures today, this is shapes and geometry of surfaces, and then it's basically going to focus on topology in dimension 2. And the next lecture, which is dimensions 1, 2, 3, 4, etc., is essentially what low dimensional topology is about. And we'll give a broad sketch. So there's a reason why we flip this. In some sense, the first lecture is going to be focused on a particular kind of a problem which introduces a subject. And the second lecture will have some component which is going to basically tell us where the boundary lies. It's not, I don't think in a short span of time it's possible to go into technical details. But what we'll do is just give you a sense of a flavor. I mean, give you a flavor of, the kind of problems that mathematicians are attempting today. Of course, I mean, that choice will be biased, will be determined basically by the little bit of mathematics I know. So today is going to be roughly topology, and tomorrow will be geometry. Basically, I mean, geometry and topology used to be regarded as just one thing till very recently, and then I think it's because of the body of knowledge in each has grown to a great extent. Therefore, we have this kind of a division. But you should really think of geometry and topology as just one field. And the focus today will be more on topological aspects. The focus tomorrow will be more on geometric aspects. Okay, good. So now let's start with today's first talk. And so the title is Shapes and Geometry of Surfaces. Shapes contributes the topological aspect, and geometry, of course, as the word suggests, contributes to the geometry. Okay. So let's see. What are we really studying? So the object of study here are surfaces. Oh, before I get on with this, Please feel free to ask questions. And maybe the procedure would be that if you have a question, if anybody from the audience has a question, just raise your electronic hand. And Tejas is looking at the collection of, at you online. So if there is a question, then he'll interrupt me, and then we'll invite the question during the talk itself. Yeah, we don't have to necessarily wait till the end before interrupting. Okay, great. So let's proceed. So what are we trying to study? We're supposed to be studying surfaces. Where does this problem come from? Yeah, and let's start with a fairly grandiose notion. We want to really understand all visual information. This is basically our grand project here. Okay, let's see. So what does that mean? So when we look around us, there's a vast multitude of pieces of visual information that bombard our sight. Yeah. So here is what one sees is an unusual thing from when one is young, essentially the shape of a globe. Unusual basically because we are accustomed to thinking about the Earth as flat. Not just us, till relatively recently at human civilizational scale, as a species, we thought of the Earth as flat. It's only much more recently that we realized that no, the Earth is not flat, it's round. And this is a skeletal picture of the globe, and we start seeing this when we are young. Now here is another picture. And how are we going to understand this? This seems to be not quite fitting into standard models of stuff we are familiar with. There's something even weirder. And still further, there's this golden band spanning some kind of a green and blue stuff inside. And so let me just quickly click through these things. And so this is all samples of visual information. And they seem to have nothing to do with each other at first glance. Yeah. So what are we going to do about it? So how are we going to, so basically you have visual information. So basically that was a sample. Those 4 slides were basically samples of visual information. And what we are trying to do is organize all this information. What does that have to do with surfaces? So here's the point. So suppose you look at anything, look at a wall, look at a chair that you're sitting on. What happens? So as soon as that thing is opaque, your view is obstructed by the surface of the object. So what you are really looking at is not the full 3-dimensional thing, but you're really looking at a 2-dimensional version of what our brain tells us is 3-dimensional. Yeah. So what we really see is surfaces of objects. We think that we are living in a 3-dimensional thing, which means basically because of our stereoscopic vision, we add a certain depth dimension to things. But what we are really seeing is the surface of objects. That's why when we start learning geometry in class in school, what we really do is draw figures on the plane, and those pictures are what we are really trying to understand. So upshot, all of that stuff that we saw there, these are surfaces of 3-dimensional objects, or surfaces of what we think are 3-dimensional objects. And so we really want to understand all visual information. And by visual information, we really mean that it's the surface of things. So this is colloquial usage. Yeah. And the way we'll proceed during this lecture, we'll start with some very, very basic, not particularly well-defined notions, and then try to ask questions mathematically of these things so that the rubbish, which means the muddle-headed thinking around it, is stripped away, and so that we can get at at a precise notion that we can mathematically manipulate. So here's the thing. So what we need is basically a formal structure, a precise structure. So far, what have we said? We basically said, what are surfaces? Surfaces are visual information. And then what did we manage to cull out of the discussion so far? They are things which really are two-dimensional boundaries of things that we see in the world around us. Okay. So now, what does that two-dimensionality mean? It means that if we look fairly closely, say at the surface of a chair, so imagine an ant moving around on the surface of a chair, what it's going to see is a little round flat patch around it. And that's not particularly special to ants. As I said, as human beings, members of Homo sapiens, we used to wander around on this earth and consider it to be something flat, so locally two-dimensional. So far, we started with this very grandiose notion of all visual information. What we culled out of it is that surfaces of objects are really locally two-dimensional objects, which means we look just around at the object that we are studying, but very locally, then it's two-dimensional. Yeah? Basically, you can put a chart paper and map out various things. And now we want to organize all this information. So organize means that we should be able to classify it at some level. But then what does classification mean? What do we really mean to say when we say that we are trying to understand two-dimensional objects, which we call surfaces? So what are we? I mean, what are the parameters of understanding these things? Yeah, sure, we want to understand, but what in what terms? That's the question that we need to nail down and make precise. Okay. So here is an ideal wish list. What do? We want essentially an exhaustive list of all two-dimensional objects. So here is the thing. When we say that we are able to classify furniture into this is a chair, this is a table, this is a bed, this is a desk, etc., what are we really doing? We have a word, which is a symbol, which stands for a whole class of objects. Yeah? And so that when we pick one of them, a chair might be made of plastic, another might be made of wood, but we are going to call them chairs, which means that a chair as a word is really an equivalence class of objects which have certain common features. And so when we say we are referring to a chair, we are really referring to a chair in the abstract, which stands for some features that are common to all these things. This is not something that is special to chairs, tables, etc., but even numbers. Yeah, so we call numbers, say, for example, numbers 1, 2, 3, 4, 5, 6, 7, 8, etc. They're called natural numbers. Yeah, why? Ostensibly because they occur in nature. Yeah, but really, does the number 1 or the number 2 or number 3, does it really occur in nature? No. Why? Because what you see in nature, which means externally, you see 2 chairs, 1 table, 3 fans, 5 people, etc. So where is the number 2? It's an abstraction. It is what is common between 2 chairs, 2 tables, 2 people, 2 fans, etc. That abstraction, that common number, that common feature is what we call 2. So it's what we are really doing is we are abstracting out from our visual natural information certain common features, and that docket, which is common between 2 chairs, 2 tables, 2 fans, 2 people, is what we call 2. Yeah? We want to do a similar thing in this context of all visual information and thinking of them as surfaces. Okay, good. So what do we do? What do we want? We want an exhaustive list of all the two-dimensional objects. Now, if you had to enumerate chairs one by one, that would be a completely hopeless exercise. So therefore, we want to identify certain features which will define these equivalence classes. Yeah. So we want an exhaustive list of equivalence classes with no redundant elements. Yeah. So that means it'll be exhaustive, and there will be no two dockets which will intersect. Yeah. So if something looks partly like a chair and partly like a table, you won't be able to fit it into one of these dockets. So we want these list of elements to be mutually exclusive. Yeah. So pick up a surface, think of this exhaustive list as dockets. So this wish list basically tells me that there is a list of dockets. Think of these as folders in your computer. You pick up an object, it fits into one of these dockets or folders, and it fits into exactly one of them. That's what we really want. That's the meaning of classification. So given a locally two-dimensional object, that's what we have now. So we've now narrowed down our notion of what a surface is to something that is locally two-dimensional. We can pick something up and we want to say that it fits into exactly one of these dockets. We want to say which object in the list it really is. Yeah? As an automatic algorithm, I mean, so there is some procedural way we need to be, I mean, we need to be able to do this. Basically, we need to have a well-defined procedure for doing this. What it means, given a locally two-dimensional object, which means a surface, we should be able to go through this list and say that there is this particular docket in which it belongs. So if two objects belong to the same docket, they are the same. If they belong to different dockets, they are different. So we need a way of saying when two surfaces are the same and automatically when two surfaces are different. Yeah. So far, what have we done? Summary, we started with this very grandiose way of saying that, look, we want to classify all visual information, but then we decided what exactly is visual information. It is where it gets obstructed on the surface of the world around us, of objects in the world around us. Then we decided what exactly does that mean. If we look fairly closely, it means two-dimensional surfaces. So things which are locally two-dimensional. So here it is again. What does local two-dimensionality mean? Revisit the surface of the picture of the globe. So if you look at one of these little squares, yeah, these little squares are actually then translated into what one sees as maps on an atlas. Yeah. So these little squares, they look exactly like pieces of chart paper. Yeah, there's an x-axis, there's a y-axis. So this x and y are two, and that's the local two-dimensionality of an object. Yeah? That's what it is. Here, there's another picture of two rabbits, and there's at the corner you'll see there's this round square. What has happened there is basically there has been, I mean, you have looked at the surface of this rabbit, computer simulation of a rabbit, but up close. And so what has happened is that you'll see on this right corner picture that there are lines which are the x and y axis, except that they are not vertical and horizontal. One is maybe at an angle of some 60 plus degrees. The other is at angle of minus 30 degrees or so. Yeah, but it's still a chart paper, except that it's been turned around a little bit. Yeah. So again, the surface of the rabbit is a two-dimensional thing. Okay, good. So now we basically said, okay, so fine. Now we really want to, I think now we are pretty close to being able to give a formal or precise mathematical definition. But it starts, I mean, I think this is something that you probably should take home. I mean, mathematics is a branch of science. So you really start with empirical things and then abstract out certain features so that without reference necessarily to those formal objects, you should be able to manipulate them. So here is the thing. A surface or a two-dimensional manifold is a topological space that is locally homeomorphic to R2. Yeah? So what is homeomorphism? It's a one-to-one continuous map with a continuous inverse. Yeah? So when we say that something is locally two-dimensional, all that we mean is that it's, firstly, what are the objects we are looking at? The larger category is topological spaces, which means it has a certain notion of what is near and what is far. And every point has a little patch around it, which looks like two-dimensional flat R2 with X coordinates and Y coordinates. And what this does is this definition really nails the object that we are trying to study down. Yeah. So what we were studying, now we can actually forget where this problem came from, that we were trying to classify or understand all visual information, but we are now basically we have abstracted out the common notion, and the object that we are really trying to study are two manifolds. Yeah. So basically now it's a notion which is completely contained within the domain of mathematics, in the sense that I mean, now it's a notion which, it's independent of where it came from. It's an object which now can be defined without referring back to anything that we started off with. And this is the thing that we can really manipulate in our heads on our pieces of paper. But so far, let me just revisit the picture one more time. So here, you have this surface of the rabbit, yeah? But imagine this is made of something like, it's the surface of a balloon, yeah? So imagine that these ears have been made by tying it with strings. You have these people who sell balloons on streets with various features made out of them, and they make these features by tying various strings on parts of the balloon. But suppose you relax those, you remove those strings, what will happen is that these features will start blowing up, so you can pump air inside the rabbit, and it's going to become rounder and rounder, and it's going to become finally like a round ball. So question is, we started with saying that, we want to look at all kinds of two-dimensional surfaces, and now we are asking, well, are there other examples? And here is the answer. Of course there are. So here is the surface of a donut or a bicycle tube, and mathematicians could give it a name. It's called a torus. So what is it? It's basically, now there is this, it's not a round sphere, but it's essentially the surface of a bicycle tube. But again, it's tiled by these little rectangles. So if you look at, if again, you imagine a little ant crawling along the surface of this bicycle tube. And if you look at one of these rectangular patches, that's exactly like a piece of graph paper. Yeah, so it's essentially R2. Yeah, so locally R2, there is the sphere, and here we have one more example, the torus. And at a certain intuitive level, not very precise, the sphere and the torus don't seem to be the same object. Not the same object means that they are not homeomorphic to each other, which means that there isn't a one-to-one continuous map from the sphere to the torus with a continuous inverse. So that needs a proof, but at least at some level, the torus has this hole inside it and the sphere has no hole. And that object, that feature of having a hole inside, is something that we need to capture within the framework of mathematics. Yeah. So this is a sample of something which we really need to say is different, because there is this hole inside, and we need to have mathematical structures in place that detect this. Yeah. Okay, good. So we say that two surfaces are the same. So what did we mean when we are saying same? We mean a mathematical notion of equivalence, and that's what homeomorphism is. So we've already said this, but let's say it precisely. Two surfaces, S1 and S2, are homomorphic if there exists a one-to-one onto continuous map from the first to the second, such that the inverse from the second to the first is also continuous. Okay, good. So this is a formal notion, but where did this definition come from? See, a definition is not something that falls out of thin air. It's only when you live with the notions and ask yourself, what is it that I'm trying to capture? What is it that I'm trying to make precise, that these notions start evolving? So the intuitive idea is the following, that the first surface can be continuously deformed to the second without tearing the first anywhere and without putting glue in and creating new features on the second. So roughly, here you have a dumbbell with 3 bells, so to speak, and then you start deforming it. You want to make it more and more uniform so that this fat stuff in the middle starts becoming more equally distributed throughout. This is actually a 2-dimensional toy example of a process which I'll come to in the second talk today, called Ricci flow, which basically is a way of saying that you are really flowing the object, continuously deforming it by, what is the surface trying to do? It's trying to say that its curvature or sharp, this is something we'll come to later on. The way it's bent in different places is more or less uniform. So what is happening is that there were these thin necks. At the next stage, what happens is that the thin necks become a little fatter, and the round bulbs at the end become a little narrower. Yeah, so the places where things are fat and round, those become thinner, and the thin parts become fatter. So it's basically a more democratic distribution of size or thickness across the surface. And then when you go further and further down, finally you see that it's actually become almost a round sphere at the very end. And it's a theorem which basically says that if you start with something which is homeomorphic to a two-sphere, and you run this process of distributing curvature, distributing this bentness over the surface, in the limit, you will always end up with a round two-sphere. So there's a process of doing this. So there's a continuous deformation is what is the way of thinking about homeomorphism in intuitive terms. Okay, here's another example. There's a rather crinkly lemon at the left. That's this 1.0. And then you start moving it smoothly. At the right-hand limit, you get a round lemon. Okay, maybe are there any questions? Yeah, seem to be some questions. How would be this as definition of homeomorphic? A light source in shape of S1, it can completely illuminate S2, assuming S2 is inside S1. Then both can be homeomorphic. So firstly, there is an undefined notion here. What is a light source mathematically? That's one problem. Suppose you can even do that. You can fit a torus inside a sphere and then the light will completely cover. Yeah, something which emits light. Light is not a mathematical notion. That's the problem. Light is a physical object. It's not something that is mathematically well defined. So we really, yeah, okay, good. So this is the only thing. So it's essentially you need to abstract out from physical reality something which can be defined purely in mathematical notions without reference to the physical source. So light is not well defined. Light, yeah. So there are ways of saying this, but then one will have to get into what is a geodesic, what are straight lines, etc., etc. We'll come to that when we are studying geometry. Okay, good. So let's proceed. So this is what is an intuitive idea about homeomorphisms. Okay, good. Way we think about it is continuous deformations. But please feel free to play with whatever definition that you've come up with, so long as you can abstract out the physics or physical reality from it and and have a well-defined mathematical notion, maybe you'll come up with a definition which is different. And then you'll be able to play with it. Okay, good. So, but I think this question is illustrative because very often we really tend to conflate physical things with mathematical entities, and till such time that as we have stripped away the physical dependency, it has not really become mathematics. So I mean, it's not that, I mean, there's some common understanding that at a certain level, you should be able to describe it purely in terms of sets. Yeah. The sets are the fundamental undefined objects that we play with. Yeah. So those are accepted and we have some intuitive understanding of them, and then we go on from there. Okay, good. So now, what are we trying to do? As we said, we want to understand all visual information, by which we meant that understand all two-dimensional surfaces, and we have some understanding of what understanding means, which is basically a classification, which means an exhaustive list of dockets, so that if you pick up one of these surfaces, and then you'll be able to plonk it into exactly one of these dockets and one of these dockets. Yeah. So that's the problem that's there in front of us. So classify all two-dimensional information. So let's see. Let's do an experiment. Yeah. So there's a physicist. I mean, there's a mathematician who's passed away, V.I. Arnold, who basically described mathematics as a branch of science where experiments are cheapest. So we'll perform one of these cheap experiments here. So here is something that we've pinched off the internet. So here are 3 pictures that I'll show you quickly. Yeah. This last looks like a teapot with 3 handles, except that it's closed. You can't really pour tea into it, nor can you extract tea out of it. There are these 3 things. Yeah. Question: are these 3 things the same, or are they different? Here is the first object, second object, where the holes seem to be all aligned up along a particular direction. And in the third, there is this fat round thing in the middle with 3 handles attached to it. Okay. So what are guesses? Okay, good. If 2 surfaces are homeomorphic, could we continuously deform one to another? Always. A great question. There's somebody called Srijam Das who has asked this great question. I have actually glibly said that the intuitive way one thinks of it is deforming one to the other continuously without tearing. Yeah. And but they have actually nailed a precise question here. If 2 surfaces are homeomorphic, could we continuously deform one to another always? Aha. And the answer is yes. The answer is yes, except that I have not defined what deformation is. Yeah. And that's a whole world unto itself. Yeah. For the time being, let me just illustrate the answer to that question by these 3 pictures. So great question. If 2 surfaces are homeomorphic, can we deform one to the other by continuously? Yeah. So let me give you an answer here for these 3 pictures where the answer is yes. And I wish I had pictures here where I could give you an answer no, but from a restricted notion of deformation. Okay, so what's happening? So imagine this. So you look at this rightmost handle that's poking out of this three things. So think of this as this fidget wheel, yeah, spinner. So essentially, you look at the right thing and assume that this whole thing is made of something rubbery, say plasticine or something like that. And you can take the rightmost handle and you can push it inside slowly. And I mean, imagine this next picture. It's actually arranged in the other rotated by 90 degrees. What has happened is that you've taken the middle handle of this, the first picture, and you've pushed it inside. Yeah, pushing it meaning basically from the right side you want to push it inside towards the center, so that at the end you get this picture with three things lined up with each other. I'm giving you a very hand-wavy, intuitive explanation, but it's basically the aim here is to convince you that the first can be obtained from the second can be obtained from the first by deforming continuously. And if you can deform something to something else continuously, you run that backward. See, mathematicians don't have this problem of physicists that time cannot be run backwards. Yeah. So if you can in forward time deform first to the second, then you just flip the direction of time and it's going to deform back. Yeah. That's all. So if you can deform the first to the second, you can deform the second to the first. So this is first and the second. What about the third one? Imagine this fat part in the middle and you flatten it out. What are you going to get after just flattening it out? You're going to get, I mean, essentially this middle part of this three guy, if you blow up just the middle part, you're going to land up with the third picture. Yeah. So the third picture, by blowing down this fat part in the middle, you're going to land up at the first picture. And so therefore the first picture can be, and the middle part can be flattened out and you can get the third picture. And then by pushing a handle in, you can get from the first picture to the second picture. Okay, good. So which means these three things are deformable into each other. As we said, what we are really doing is deformability of one to the next is really an equivalence relation. Yeah, that's how we will have to come up with a precise notion of deformation. It really means that there is a continuous parameter family, yeah, closed interval 0, 1's worth of maps, so that the first map gives you the first picture and the last map gives you the last picture. Yeah, and at each stage you have deformed without tearing, without pasting. That's a precise notion. For those who are familiar with this, So this is an irrelevant thing in physics. Also, most of the theories obey time reversal symmetry. That is perfectly correct, but entropy does not. But here, nothing is. I mean, this particular notion is not relevant to this. So the physical, what we are trying to say is that the physical notion of time is irrelevant to this discussion. Just as the physical nature of light is irrelevant to the notion of a homeomorphism. Yeah, that's the point of these questions, this stuff. See, essentially, you have to really abstract out from physical reality certain features which you can put on the paper as abstract notions which can be manipulated in and of themselves. You can go back to physical reality to test your theories out and ask whether they are relevant to physical nature. What I'm trying to stress is that unless you have abstracted out something from that physical reality, what you're doing is not mathematics. Yeah, it's science, certainly. But there is a way of thinking within mathematics which is basically you abstract out something, put it in this self-contained way, and then manipulate it purely using logic. Yeah. So what we are really doing is, as we said, that so the way of thinking about it here is that the first can be deformed to first map of this object into three-dimensional space can be deformed into the last object by passing through deformations. In the picture that we had we had shown earlier, this deformation is being done inside three-dimensional space itself, and that's the real catch. So there was this question whether something can be deformed if two things are homeomorphic. Can they be deformed one to the other? It depends on how you define deformation. It depends precisely on how you define deformation. If you ask the question, oh, these are objects sitting inside three-dimensional space, and you can deform them within three-dimensional space from one to the next, then the answer is that there can be two things which are homeomorphic. They are both sitting inside three-dimensional space, but you cannot deform from the first to the second through objects sitting inside three-dimensional space, all homeomorphic to each other. So the answer to that question that you asked, whether one can be deformed from one to whether if two things are homeomorphic, can they be deformed one to the other? The answer is no, if you demand in addition that they are all the way embedded in three-dimensional space. On the other hand, if you are requiring them to be just deformations of maps, continuous maps, yeah, then the answer is yes. Yeah. So that part of it is okay. Just as abstract continuous maps where you're where the space where you're embedding is not important. Yeah. So the target R3 is not a constraint. So here is the basic point. I mean, the object here is intrinsically defined. A sphere is something which is homeomorphic to something which has an equation x square plus y square plus z square equal to 1. That's a topological definition of a sphere. Just something that is homeomorphic to it. Then your ambient space where you are making it sit is not relevant. In that specific sense of deformation, the answer is yes. That's the point. Yeah. So if the notion of an ambient space is brought in, then the answer is no. If the notion of ambient space is irrelevant, then the answer is yes. So the answer to that question, can you deform one to the other? Always, if two things are homeomorphic, it basically prompts us to probe what is the notion of deformation. Okay. So we have this example here where we saw that it's basically like a teapot with three handles. Okay, there seem to be some more questions here. What does it mean for embedding in a space? Can you give an example of a surface embedded in an ambient space? Excellent, excellent. Yeah. Oh, there is a what if the middle part in the third picture is hollow? Then it won't be homeomorphic to first one, right? Or all things, as Tejas has pointed out, all things are hollow basically because, see, as I said, we are really not looking at, we are looking at only the surface of objects. So there is nothing inside. It's really, as I said, as it started off, it's only the visual information, which means if there is something solid, then is it locally two-dimensional? No. If an ant moves around on the surface of this, the only thing that ant sees is the surface. There is nothing else. There is no, I mean, so basically this is an exercise in that abstraction that we were talking about. We have to remove from our minds that, okay, our brains have told us, oh, there is this third dimension, etc., etc. We need to decondition ourselves to basically think of this as intrinsically two-dimensional. Okay. And there was something else which basically asked us to define embedding. Okay, what is an example of something that is embedding? This picture. So it's a teapot, it's a surface of a teapot with three handles, or even more simply, let's look at the globe. Yeah. So it's basically, what is it? It's a collection x square plus y square plus z square equal to 1. The solid object, which was again the other question, is x square plus y square plus z square is less than equal to 1. But we are really looking at only the surface x square plus y square plus z square equal to 1. Yeah? That's a surface. That's a surface. That's a two-sphere. And this map, which takes a point on the surface of the sphere and maps it to the coordinates x comma y comma z inside free space, is the embed. Okay, good. And so now, once we have now realized that these three things, these three pictures that we just showed are deformable one to the other. So they are homomorphic. And so now we are, I think, in a position to state what the fundamental theorem of some of these surfaces is. We are not, I mean, we started off with a very, very grandiose view of classifying all surfaces. Yeah, well, typically these problems are kind of ill-defined. I mean, because the word all is not something, well, it means basically locally two-dimensional. And if you really are that ambitious, in a very formal, precise sense, what will happen is that those guys will not be classifiable. Yeah. Because what we needed were these countably many dockets. Yeah. So here's the point. We impose certain conditions basically because when we look at the world, we are really looking at some finite part of it. So we impose that as a precise condition. So if you have a closed surface, closed means basically the surface is trapped within a finite amount of space, roughly. And there's one more object, one more notion, the notion of orientability. So I'll say what this is in a moment, but this is a hypothesis, a crucial hypothesis. But if you look at closed orientable surfaces, then you can really create dockets. Just create dockets by numbers. Create dockets by numbers, which means basically natural numbers union zero. Yeah. And the theorem, this is a 19th century theorem, basically says that if you take a closed orientable surface, it is exactly homeomorphic to a sphere with n handles for some non-negative integer n. What is n? In this previous picture, this n was 3. So you had a sphere, which is basically what we were referring to as a teapot with 3 handles. And outside that, there are these 3 handles attached to it. So there's a spherical base, and there are these 3 things attached to it, which give rise to the number 3. If there were none attached, 0, then you would get back the sphere. And what this theorem is basically saying, that you pick any surface that you look at, which is 2 things, closed and orientable. What is orientable? Basically, the intuitive idea is something that can be embedded in 3-dimensional space, which means really all our visual information, so long as we are looking at something that is strictly contained inside a finite amount of space, it is going to be exactly one of these. Yeah. So a closed orientable surface is going to be homeomorphic to a sphere with n handles. N could be 0, 1, 2, 3, 4, etc., etc. So which means what have we done? We have now created dockets. The labels of the dockets are 0, 1, 2, 3, etc., etc. You take any closed orientable surface that you see, it fits into one and exactly one of these dockets. This is a complete classification of closed orientable surfaces. Why? You take something off the shelf and says, oh, it has, what is the number associated with it? Oh, it's 49 or 71, whatever. So you take that number and then you say, okay, it fits into this docket labeled 49 or it fits into this docket labeled 71. Take a second one, maybe it fits into some docket, new docket called 56. Since 56 is not neither 49 nor 71, the new object is different from the first object. But if a third object again fits into 49, it will have to be homomorphic to the guy called that, to the previous guy which we had fitted into the docket called 49. So this is a full classification. It's completed our wish list. We had dockets which have labels. Now they are labeled with 0, 1, 2, 3, etc., etc. and you pick an orientable surface, closed orientable surface, what this theorem says, it fits into one of these dockets and it fits into a unique one. But I need to elaborate a little bit on what orientable means. An orientable basically means that it has well-defined sides. There is an outside and an inside. Yeah. So all these things that you were seeing in the previous few pictures, we were looking at things only from the outside. And somebody was suggesting, what if it was solid? That solid is really, what you are thinking of as solid is really the inside of the surface, which means that an ant, it could do one of two things. It can crawl on the outside of the surface, and if it's a hollow sphere, it can crawl on the inside of the surface. But an ant crawling inside can never come outside. An ant crawling outside can never suddenly go inside. There is a well-defined side. Yeah. More precisely, there is a well-defined direction to the normal to the surface. So let me just elaborate this on this particular aspect of things. Here is a picture. So basically by this painter called Escher. This picture that he's drawn is what's called a Mobius strip. Yeah. The Mobius strip is not closed. So I'll come back to that point in a moment. But what he has drawn is these ants are crawling. So if you look at the first ant, yeah, right at the top, I mean the topmost ant, that's the starting point. Imagine that its middle legs pointing vertically upward. That's a normal to the surface. Now start following the ant. So you go round and round. This is called a Mobius strip. You go round and round and round. And then you see that you've landed up with another ant, which is almost at the same point as the first ant, except that its legs the vertical legs are pointing exactly in the opposite direction, which means you can continuously move along the Mobius strip, and suddenly at the end, a normal outside the surface, which was pointing in one direction, when you go around, it is now pointing in exactly the opposite direction. This feature of having a normal pointing in opposite directions by moving around on the surface is exactly what captures non-orientability. It means that the Mobius strip does not have well-defined sides. There is no inside, there is no outside. Let's come back to this other thing that I had said, that the Mobius strip is not really closed. Why? Because you can see that there are boundaries, right? It's like if you take a little strip of paper, you paste the one end of this to the other, what are you going to get is a cylinder, which means that there is a top boundary and there's a bottom boundary. So if there are these boundaries, then we don't say that the surface is closed. On the other hand, you can take the two boundaries of an annulus and you can paste them together, you're going to get back to a torus. Yeah, that's closed because there are no boundaries. A Mobius strip has a boundary, and that boundary is a single copy of a circle. Yeah. So basically, if you trace your finger along the boundary of this Mobius strip, you're going to see that you're really going round twice and then closing up. So you're going to get a single circle as opposed to the case of a cylinder. The boundary of a cylinder is two circles. The boundary of a Mobius band is exactly one circle. Okay, so were there any other questions? Yeah, there are some other questions lined up. What is the middle part in the, what if the middle part in the, no, this is already done. Okay. For these surfaces, we are not assuming that they're embedded in Rn. So what do you mean by capture limited space of closeness? Okay, good. Excellent question. Naveen Singh Rana. What exactly do I mean by closeness? First hypothesis that is that it's a manifold. Yeah. It's a manifold, which means that every point has a small neighborhood, which is homomorphic to R2. What is closed? It's a compact space. Compact space means what? You take any cover by these little patches, there is always a finite subcover. You can always cover it by finitely many patches. I mean, any cover there can be a refinement which consists of only finite time. So that's it. Closeness, think of it as just compactness, nothing else. So here the classification is of compact surfaces only, right? Or are we classifying all closed spaces? As I said, compact surfaces are exactly, a closed thing is by definition compact. Yeah. Okay, good. Mobius strip I've already demonstrated for those who know if it is compact and without boundary. Yeah. Okay, good. Excellent. Great. So all these things have been answered. Good. So this is an example of something which is actually, if you include the boundary, it's not really a manifold. At the boundary, it does not look like R2. So strictly speaking, a Mobius strip, as seen here, is if you remove the boundary, it's not closed. If it's not compact. And if you include the boundary and you make it compact, then it's not a two-dimensional manifold in the strict sense. However, this can be slightly modified. And here's a picture. Basically, this is a picture of what is called a Klein bottle. So what has happened is that you've now taken a long annulus and you've taken one end of it and glued it to the other end by flipping the orientation. But in order to do that, you could do it if you glued it end to end, you would get a torus. But what you've done is you flipped it with the opposite, with a different orientation. So in order to do it, insert it inside three-dimensional space, you will have to cut the surface at some place. So it's really cutting itself along a little circle, and then only can you glue it inside three-dimensional space. And imagine that you can actually live inside a higher dimension, which means the fourth dimension, where this intersection can be removed. Just as you have two strings crossing each other in two-dimensional flat plane, add on the third dimension and just lift the point of intersection of the upper thread, and then it gets embedded. Yeah. So this Klein bottle here, this is what's called a Klein bottle. It can be embedded in four-dimensional space, but in three-dimensional space, it intersects itself. Here's another picture of the Klein bottle, a more suggestive picture. But as should be clear, you can't really drink from this. I mean, see again, if you pour water in at the bottom, at the top, it's going to go through this channel and then going to come up on the inside. Yeah? And the thing is that this tube necessarily intersects somewhere. I mean, so you see that there's the thin tube intersects the body of the larger surface at some point. And this is a fact that if you have something that is closed and orientable, you cannot embed it in three-dimensional space. If you try to map it into three-dimensional space, there will be self-intersections. That's what this picture illustrates. That particular fact requires a proof. And I think the correct way to prove it would be using some algebraic topology. And what we've said today is basically that there are these numbers with which you can really bring your all closed orientable surfaces in one-to-one correspondence with. And we've stressed why. There were these two hypotheses in that theorem. One, closedness, and the second was orientability. And then these things feature in this. I mean, if you relax either of these, then the classification theorem does not hold in that particular form. Closed non-orientable guys can also be classified, but open surfaces, in a very precise sense, are not classifiable. Yeah. Okay, good. So yeah, let's stop here. Thank you. Yeah, if there are any further questions.
Yeah, if there are any questions, just raise your hand and you can directly put on your audio and ask Professor Mahan as well. Okay, so someone in the YouTube live thing, I've answered this some of the questions. The last question was, are there any other non-orientable surfaces other than Mobius band, RP2, and the Klein bottle?
Sure. So here is okay. So since you already know of these objects, the Mobius band is not a closed manifold, so we'll not talk about the Mobius band. But here is the thing, just as closed orientable surfaces can be built up out of handles, it's a sphere with n handles, yeah. Closed non-orientable surfaces can be built up out of projective planes. So what you do is, if you take two projective planes, you remove a little open disk from one, you remove a little open disk from the second. What will happen is that you've left with two manifolds now with boundary. Boundaries are circles. A projective plane minus a little open disk turns out to be a Mobius band. And the Mobius band has this single boundary component. So if you take two Mobius bands and glue their boundary circles together, you're going to get a closed non-orientable surface, and that is homeomorphic to the Klein bottle. This is a lovely exercise. And so what one can do is this process of removing a little disk from two sides of two closed manifolds and pasting them together. It's an operation called connected sum. Yeah. And so here is the next theorem for closed non-orientable surfaces. Every closed non-orientable surface is a connect sum of finitely many copies of RP2. That's a complete classification theorem for closed non-orientable surfaces. Yes, any other questions?
So there's some more questions on the Zoom chat as well.
Sir, are not closed all open? What exactly does that mean? Are not closed sets all open sets? Or are you referring to closed manifolds? Can you raise your hand? I mean, just why don't you
Yeah, you can
unmute yourself and ask exactly what you have to say. Here's a lovely question. What if we consider higher dimensions? Can we classify all closed orientable surfaces in that case? Excellent question. Wait for 45 minutes. And this is really the reason why I flipped the order of these two talks.
So on Zoom, the question.
Hello,
sorry.
sir.
Yeah,
Can I
sorry.
ask?
Yeah, go ahead. Yeah.
Sir, like as you said, for closed orientable, we are classifying it to an.
Closed orientable surfaces, we are classifying. Yes.
So, like if it is not closed like this, Mobius strip, will it be open? Like how we are saying something is closed or not closed and
See,
open.
as we said, that closed means compact. So if something is not compact, it's not compact. That's all. If something is not compact, if something is not a closed bounded subset of Rn, it's not compact. Yeah. So yeah, I mean, if you make your question, what exactly do you mean by open? Do you mean open as an open set? Where? I mean, in a topological space, you have closed sets, you have open sets, and you have sets which are neither open nor closed.
So
yeah.
You said we are classifying. So if it is closed, we have classified. Now, if it is not closed, like
So here is the opposite of closed here is not open. Yeah. You can call it open if you like, but the real thing would be: can one classify non-compact open manifolds? Yeah, and the answer to that will be you can do it under extra assumptions. Basically, if you know what a fundamental group is, all surfaces with finitely generated fundamental group can be classified. But as soon as you have infinite generation, then it becomes a real problem. So this theory is much more sophisticated. I mean, the theory of, it's not that other problem is not attempted, it's done. But I don't think there is any real hope of gaining a systematic answer to that question. Yeah, so you will have to impose additional reasonable hypothesis to define what exactly you're talking about. See, here is a question. Basically, you look at a sphere or a copy of R2. remove a Cantor set from it. Yeah. You know what a Cantor set is, Aryan? Do you know what a Cantor set is? Yeah, good. So you remove a Cantor set from something.
Yes, sir.
Now here is the question. It's very simple. Basically, it's the following. You take R2 and remove from it any closed subset,
Yes.
any closed set. How are you going to classify this? This is the problem. The point is that the collection of closed sets is uncountable.
Yeah.
So the notion has to be made precise before you can get at his answer, because you want a collection of, what is the mathematical definition of a deformation of a surface? Good question. As I said, it's really if you want to deform inside three-dimensional space, it means basically you have a continuous map from the surface across the closed interval 0, 1 into the Euclidean 3 space, so that surface cross 0 maps to the original guy, surface cross 1 maps to the last guy, and at each time, surface cross time t, it is an embedding. Yeah, this is called an isotopy. Okay, so deformation, actually I've used the word deformation somewhat loosely, and precise notions of deformation, depending on different contexts, they have different words for that. Okay, seems we can't, sir, you told we can't embed non-orientable surface in 3D. That's not quite right. I said you cannot embed closed non-orientable surfaces in 3D. And you said that all closed non-orientable surfaces are finite sum of projective planes. So it classifies all non-orientable closed surface in all dimensions. No. There is no all dimensions. I'm just talking about 2 dimensions, right? Embedding is a different issue. A locally 2-dimensional thing is the dimension of the domain. The dimension of the target where we are embedding it is not relevant here. It's not something that we can embed it in R3. It's a fact that we can embed it in R4. That's all that I said. So the dimension of the embedding space is not really relevant here when we are asking about a classification of surfaces. We are really asking for an intrinsic classification. Again, classification work in high dimensional spaces. Wait for 45 minutes. I will address exactly this question. Yeah.
Someone on YouTube live is asking, if open surfaces are not precisely classifiable, then how do questions related to them are being answered today by mathematicians? And what kind of other questions can be asked about?
Because, very good, excellent question. Because those problems actually arise in other fields. So for example, in complex analysis, R2 can be actually identified with the complex plane. So you have extra structure. And then the notion of a complex plane minus closed sets now makes sense. And you really have this additional structure that you want to play with. So basically what's called a conformal or complex structure. So it depends on the context. Here we have given one context. That context is called topology. But then you can enrich your structure and then ask the same questions. So the questions are, by the way, it does not mean that if you can ask a question, you will be able to answer it very promptly. Tomorrow, I'll talk about some problem in geometry, which basically took some 2000 years to solve. Okay. Can orientation be viewed as a topological property? Yes. But I don't want to give the answer now. Yeah, right. I mean, N is basically called genus. So this, it's not basically. Basically, this is what it is what we described today. Then you give it a name. You call it genus, you call it something else. It's a characteristic number, whatever. That's something that you associate with it afterwards as post factum. That number N has a name, it's called genus. That's all, nothing else. What is the definition of boundary here? Good question. It's basically collection of points in this thing where where a neighborhood looks like an upper half plane along with the x-axis, but does not look like a flat arc. That's the notion of a boundary. Okay. Please give the definition of a projective plane. Take the round sphere S2. Take antipodal points on that, which means x, y, z, and minus x, minus y, minus z, and you paste those pairs of points together. The formal notion goes through what is called quotient spaces. Equivalently, you look at the collection of space of lines through the origin in Euclidean 3 space. Good questions. If two surfaces are homomorphic to each other, then the surface orientation will be preserved, of course. Yes, that's answer is correct. Yes.
So Jagadishwar has asked, can orientation be viewed as a topological property?
Yeah, I answered that
Yeah.
question. Yes. Yeah. Okay. So if gluing and cutting are not deformations, what kind of functions are they? They're not functions. It's yeah, I mean, the correct way to look at these is through the framework of quotient topology. I really strongly recommend that those of you who are really interested in pursuing this further, go back and look at this chapter on identification spaces in this little book by M.A. Armstrong. Yeah, it's called Basic Topology. Go and read that chapter. Then this framework of quotient spaces, which is really what forms the background of this cutting and pasting, that will become clear to you. Without that, we will not be able to talk precisely about these cutting and pasting. Okay, so maybe if there are any relationship between the dimension of a surface and the minimum dimensions required to embed the surface. Excellent question, excellent question, excellent question. The surfaces that you classified has no boundary. That's correct. That's correct. In relation between dimension of a surface, yeah. So the point is closed orientable surfaces can be embedded in R3. Closed non-orientable surfaces cannot be embedded in R3, can be embedded in R4. That's the quick answer to your question. Of course, classification requires countable possibilities. Otherwise, you can actually, okay, fine. It's in principle, no. But then you'll have to have an index, and then that number you'll be able to, should be able to. In principle, yeah, I mean, ideally, when we talk about classification formally, it's a choice of a definition. Yeah. So there are things which are parameterized by positive real numbers, and for example, things like conformal structures of annuli, etc., etc. And there the classification does take on continuum many values, but here we are really talking about countably many.